Okay, welcome everyone. It's a pleasure for me to be able to introduce the Forskningsdagene 2020 at NTNU in Gjøvik, and a special welcome to Ivanna Baturynska, and also welcome to you sitting here in the audience, and to those of you following us by net. Ivanna is from Ukraine, and she defended her thesis, Machine Learning of Quality Assurance in Polymer Powder Bed Fusion Additive Manufacturing, in April this year. The latest developments in the field of additive manufacturing, AM, have led to the wider use of this technology for the production of end-user products. As a result, more stringent requirements are set to the quality of parts produced with AM technology. In order to satisfy the needs of industries and to make additive manufacturing more attractive technology, a more in-depth understanding of the factors that cause variations is needed. This thesis aims at describing two perspectives. For the first, gaining more knowledge about the effect of build layout design on the quality of the produced parts, and secondly, how the obtained knowledge can be transformed into a user-friendly decision support tool to minimize variations in polymer powder bed fusion process prior to fabrication. The work was done at the Department of Manufacturing and Civil Engineering. Ivanna's talk will be in English, and it's also been streamed. Questions may be asked in the chat rooms, in English or in Norwegian, and I'll bring them on to her to answer after her lecture. So, Ivanna, the floor is yours.
Thank you very much. So you heard many words that can be a bit strange and unfamiliar. So today's my approach on the presentation will be completely unacademic. So I will try to explain you why I did my PhD study and everything that Gun presented, but in a more easier way, and by using 3D printers that actually desktop 3D printers that you can buy in Clas Ohlson, for example, and how based on the same issues that are present there and how we resolve them. So I called the presentation 3D printing right the first time, since many of you probably have heard about additive manufacturing as 3D printed, that it's a great technology that helps us to make great products. But the question is, do we actually can do it right from the first time, or do we need to produce one part many times to get it in the quality we want? I want to add a bit more on my background. So I actually come from Ukraine. I moved to Norway 7 years ago to start my master's study in sustainable manufacturing. And after that, I actually went for PhD at the same department and continue working there. In Ukraine, I also finished my master in computer integrated manufacturing, and I have my bachelor's from automation and computer integrated technologies. So all this mix comes together to the solutions that I'm developing. So I work not only on additive manufacturing, but I also am interested in traditional manufacturing, and my focus is on data analysis, machine learning and stuff. But today we will look a bit on different side. Today we will talk what is 3D printing in a simple words. How do we define quality? Because you will see that every single person can have your own opinion on what is good quality and what is bad quality. Which factors affect quality of 3D printed parts, And are there any design rules? Should we follow some rules to get a good parts? I will also show you some examples on the printing settings, how can we manipulate them and how they will affect your result. And then we'll move slowly to the industrial additive manufacturing, and we'll show you the difference between desktop 3D printers and industrial machines. And I will also tell a bit more on the current research. So what do we do in our department and in our laboratories in the Gjøvik? So what is 3D printing? 3D printing is a technology that allows us to produce 3D objects by joining material layer by layer. And to do that, we need to have a 3D CAD model available to produce the parts. So now you can see a small video of how actually a desktop plus a 3D printer, we have more than 60 of them in our lab, how it actually works. And then on the picture you can see how by using these technologies we printed a soft toy of the pug, mops, in different dimensions and different colors. So this is a fun stuff. But actually, what are the main components of 3D printing and additive manufacturing in general? In general, we can say that we have three main components. The first one is the CAD model that we design. Then the second one will be material, depends on the technology that we use. And then the third one is actually equipment, machine itself, everything that brings energy to melt material. And it's very important to understand these three different parts, because each of them, they contributes to some positive and negative effects on the production of the parts. And at the same time, we also need to know what is the synergy of them, how to control and change some of them. And I will show you later about that. If we talk about CAD, it's especially those who know how to draw on the paper. Maybe at least once in a life you draw on the paper. But when we talk about CAD model that we use for 3D printed, it's not a 2D as you can draw on the paper, it's a 3D image. Typically for those we use a special drawing software, which can be SolidWorks, Autodesk, and so on. Depends on the country and accessibility. But in reality, we don't just take a 3D CAD model and print it right away. We do some manipulations. First of all, we save it in a special resolution, which is STL file. STL file transforms the 3D model from the solid 3D shape to a 3D surface-based shape. So then we have triangles, as you can see on the picture, that actually helps us to describe this surface. And then these triangles allows us to slice the object. So if, for example, we have an object, in order to print it as it is, we need to slice it in 2D slices, and then each slice separately is printed out one by one. So this is what you saw in the first video. But then the question is, okay, we understand that we have a process, we have material, and so on, a lot of choice. But what is quality? Before talking how to set parameters or how to evaluate and improve them, we need to define quality. What is quality to you? Is it a quality that is a bad quality the case as you can see on the screen when you have, we call it pasta printing, when instead of having a final object, you just, it happens some error by some reason, and then you can see this kind of pasta behavior. You just put it on the plate and eat, but you don't eat it, of course. Or maybe for you a bad quality will be if you want to produce some part and then you have these like small pieces of melted material that is a bit too much and it going off the layer. Is it a bad quality? Or maybe if we talk about printed object, I don't know if it's a good on the screen, but you can see here it's also something is like the surface is not as good. Is it that bad quality? What do we call bad quality? What is the definition? So for us humans, the definition of the bad quality in the daily life, it could be that it doesn't look nice, it doesn't function as it's supposed, But in industry, we have much more complicated definition of the quality. There, quite often, we focus on the dimensions, and then small deviations are extremely important. But in everyday life, who cares if you print a minion and it's a bit smaller or larger? Who cares? No one cares. You want to have it look nice, right? So then you will focus on a bit different settings, and then you will have a bit different problem to solve. So then when we talk about quality, and I will tell you slightly what can affect the quality. So we can think about rain. Yesterday it was rainy day in Jorvik. Does it affect if I will set a print on the rainy day? Is it gonna affect my quality? Or is it okay if it's outdoors, it's raining, and I just set the print? Or maybe should we choose a sunny day to do that? Have you thought of that? And then I can say you for sure, in the research we already observed, and in practice we observed that on rainy days we actually have much worse quality than on sunny days. And it especially about the surface. So when you have these stripes of the material, white one comes out of the surface, quite often we get many of them when it's raining outside. Even though we do printing inside the house or inside the lab, we still has these issues. And then when it's sunny day, we use the same CAD model, we use the same printing settings, we use the same printer that stays in the same room, but the surface is perfect. So then it means that it actually affects. So we need to take care of that, right? But is it the only things that affect quality? Most probably no. As I said to you, the way how we set our printer, so the parameters that we choose on our printer, in combination with the CAD model and material, can also lead to many problems, issues, and bad quality in the result. In some cases, it can just burn material, and then you will have a lot of burn pieces on the object, just because you use temperature that was too high. That's all. If you have a table of the printer that is too cold, most probably you will never finish the print because it will just curl up, not be fixed on the printer, and then on some of the moves, it will just continue going and following the printer head, like dancing on the table. So you can turn on the music and just have it there. And you don't want to have that, right? So then you need to be aware about this. Material choice. Yes, which material? Who produced the material? Is the material inside this road is a good one? Or maybe there is some empty spaces that will lead to some empty spaces in your part. Can you check it? Most probably no, but industry will check it. So they will try to make sure that they use correct material. And then CAD model itself. How do we design the part? This is also, we have rules that we need to follow, or at least we need to be aware of them. So then when we put all these things together, we know how to manipulate them. So the CAD model is also important in all of these parts. So can we then say that we have some factors that are controllable to us humans, and then some factors that are uncontrollable to us? For example, rainy day, can you control it? No. If you're in lab, of course, you can buy a lot of equipment to set up the control of the humidity level and temperature and so on. But in real day life at home, no, I don't think so. You are gonna do that, right? So then maybe sometimes if you know that we produce something critical, maybe some design piece that we want to stay in the living room when guests come in and we want to have it good, so maybe we can think about printing it and the times when it's not as rainy, or so just to be aware of what can happen. But then process parameters and CAD model, this is what actually we will talk about, because this is what we can control. So just an example, it's a bit far away of what we have in the lab, but still. So you can think of two parts of additive manufacturing. The one that is for home use, it's a desktop 3D printers, and then industrial machines. They are larger than me staying here, so they stay in special rooms. And it could be also used robots, as on the picture, just showing you the difference between the complexity of the home user printers and industrial ones. But now we'll talk a bit about design rules that actually are available online, so you can find them. There are many different websites that gives you this information, and some of them I will question, and I will show you why I question them. So not always we can just fully trust on everything that is on the internet, and I will show you why. But these rules work. So for example, we know that when we design some part, and if you imagine that we'll have some wall like that, we know that this thickness needs to be more than 0.8 millimeter. If you will try to do it less, you will never print it, because printer need to be able to go at least 2 layers together to make a wall. Because the printer nozzle, usually it has 0.4 millimeters, so it means the diameter of the melted material that flows down is 0.4 millimeter. So if you set your wall to 0.7 millimeter, it means that you are not able to do 2 runs together, so you don't have anything to melt together. Then you have only 1 line, and you can imagine if you just try to go 1 line on the another line, it doesn't provide you any structure at all. Any structure, so you cannot make it. So it's quite okay rule, so we can agree on that. Then we also know that if we want to have some feature, some design shape that goes up to 45 degrees, we don't need to have a support structure, so we can build it as it is. And this is important to know, because then the surface will be much better, and I will show you examples what it means not as good surface. Another rule that is about embossed and engraved details, there is limitations where we need to start from which point on the width and height. It's 0.6 millimeter and 2 millimeter. Then horizontal bridges that we need to start from 10 millimeters. We also have a size of holes that needs to be larger than 2 millimeters, otherwise it will be just a solid piece of part. You will not be able to have a hole. If you want to have a part, this is actually a very great possibility of additive manufacturing. So if you want to produce something that is 1 piece movable part, you can do it in 3D printing. But you need to make sure that the distance between these 2 connecting parts are at least 0.5 millimeters, at least, or a bit larger, because otherwise they will just melt together. It's gonna happen. So if you have less distance, it will be just as a solid part and not movable one. Then pin diameter is the same rule as about wall, that it needs to be larger than 3 millimeters, otherwise it's not gonna be able to put the structure as a piece block, and some other features as well. So as you can see, there are many design rules. They sound as something, oh my gosh, it's so hard. But in reality, if you like to design and you just play around with that, it's not that hard. You need to try and work on that a bit more. But let's talk on build orientations, because this is what we can do even if we don't control CAD model. So if, for example, we go to the web page, we find, as I did, because personally I hate to draw, so I don't use CAD. But you can download many different CAD models that are available on free websites. You just register there and then you get it. So then we just need to know how actually to build it. So this minion chess queen, do we produce it like that? Should we change the angle? How do we know what to do? So we need to have a bit of understanding of the effect. Actually, this object, this is my example piece. So today everything will be about minions. So imagine that we have this queen minion, and then we have question. So for example, if we have a build plate and we decide to orate our queen like this, because it looks like if it's gonna be laying like that, it's gonna take less time, right? It's like if you get the feeling, less layers, so it's supposed to go faster. And we can see, yes, it's 2 hours, 46 minutes to produce it in that way. But then I was like, but what if I just in the same position, but I will just orient it by one axis to have it with the eyes up? Is it gonna affect the time? Yes, indeed. It's 2 hours 45 minutes. Okay, what if we say that we want to produce it like that? So we again turn it a bit. In another orientation, you have this picture. So I'm just following pictures on the screen. Then you have 2 hours 41 minutes. Why? Is there any difference? It does look like similar stuff, right? Strange. And then I say, okay, I'm just crazy. I decided that I want to make it like that. I just want, and that's all. I want to have it standing on the crown. But it's gonna take 4 hours 37 minutes. Why? Because we have more layers to go over. So this is the reason why it's almost doubled in time. But then interesting fact that actually when we turned it like that, it's gonna take 3 hours and 28 minutes. Is there a so huge difference? Why this happens? Why time changes so much? The reason is because when we produce it in different orientations, we use the support structures that allows us to make parts that we want. Of course, as you can see, depending on the orientation that I picked, you have a different number of support structure that is required to produce this part. And then the question is, can we say who is the winner? Can you choose for yourself which one should you go for? If you use just the time as a main requirement, probably you would go for that one. It takes the least hours to make it, probably, maybe no. But then another question is, can we produce it with or without support? What is gonna happen? So quite often, the main task that we have is to find such orientation that gets as least as possible supports. But also not always it's so easy to see. So yesterday at home, I just made a smaller versions of the same minion, chess minion. It takes 1 hour 12 minutes and 1 hour 22 minutes to make them. And I wanted to test how support and without support is gonna affect. So maybe this will help you a bit. So you can see on the picture, this minion that is on the left side probably, it's with this required support. And then on the right, it's without support. I was like, I don't care about the rules, I just want to see what happens. If it doesn't print, then it doesn't print. But I don't know if you can see it, but actually there is a small difference. Without support, we got a small curling in the hands of the minion because it was hard for material without support to stay in place. So that's why it moved a bit, but the following layers were actually used this curling as a support and then continue going as okay. So that's why when you know the design rules, I was expecting this, so I knew that it's gonna happen. But also I saw that the crown is following this 45-degree rule, so that's why I went for without as well, so no support. So this is a small kinda, how can you test if you know that the CAD model follow design rules, so then you don't use support. But if you don't know that, what to do then? Then we talk about process parameters that also can help us, and support is a part of that. Not only support actually who affects the time, but there is also such thing as infill rate. What means infill rate? It's kinda connection of the walls inside the minion in our case. So I tried to make pictures from the software. I used the same layer just to show how it differs when we change the infill rate. So for example, in the first case, this is where I say I don't have any infill material inside. So I just want to have contour printed, and that's all. So it will be light, and I don't want to, I'm not gonna press it or like just damage it. So that's why. But what if we use 5%? Then we have this small triangle that appears. And actually these minions are printed with 5% infill rate. They are light, and afterwards we will put them next to the cleaning wipe, so those who wants to see and are in person, they can see, look at them. Then we move to 10%. You can see it's a bit more material that comes inside. And then when we increase in fill rate, I didn't show 100% because 100% it means that it's just a solid part. It's gonna be heavy because material has weight, and it takes a lot of time. So each of these lines, so you need to understand each of these lines printer needs to go through at each layer. And this is what affects our printing time also a lot. So then you can see this process. And then the support that I told you there is actually 4 different options that we can choose from. So the first one, it's non-support. So I told you one of these minions are printed like that. Then we have a second one, it's a support only on a build plate. That actually this one was another minion was printed with this option. Then we have a third option, is support for enforces. It means that it's you who push. If you're an expert, you can decide in which regions you want to push support. But in reality, if you don't do this, it's gonna work in the same way as non-support. So if you are not an expert and you just click on that and you didn't set the rules, it's not gonna work. It will work as a non-support. And then the last one is everywhere. So for those who are online, they can try to do it in chat. For those who are sitting here, at least for yourself, can you guess which of these pictures, like A, B, C, D, correspond to which of the options of the support? I will give you a couple of seconds just to try to guess. Okay, and now slowly I will show you what are actually the result. So the first one corresponds to D. As I said, none. I think that it's okay if you picked A instead. It's not as different. Then B, it's about support only on a build plate. So this is what I used. As you can see, it's not that much material that is used, and it was quite easy to clean it off. Then support for enforces, it's A, so it's the same as none. So if you picked otherwise, it's okay, doesn't matter. And the last one, everywhere. And actually, I used everywhere when I was producing this large minion queen. And those who are sitting here, they can see the difference afterwards. I cleaned it as much as I could. It takes a lot of time. It's very hard to do that when you use too much support. So that's why when we work with 3D printing for desktop printers and some other industrial machines, it's very important to choose orientation in the way that will produce us the best quality and minimize the support at the same time. So it's kind of a small optimization problem for our head. More experience you get, easier this task become. But then there is also another issue, dimension and tolerances, as I said in the beginning. So it's a very special topic for me because I work with this topic a lot. This is my key thing. This is what I'm looking all the time for. And that's why I couldn't just go pass by desktop 3D printers and check, is it the information that is told by different people, is it true or no? So if you will Google in some websites, you will find that they say that tolerances for desktop 3D printers quite often is plus minus half centimeter, yeah, 0.5 millimeters. The question, is it a lot? No. For home using, probably no. But then I decided to question, is it actually a true story? Is it actually this value? Am I sure that if I'm gonna use a preset printer, it's gonna produce me a part that will be not larger than these values. And in reality, no, it's not correct. So this is a sample that typically I work in my research with. You can see it on the screen as well. I used it quite a lot in my PhD study. I analyzed over 1,500 of those, so quite a lot of work to do. But in reality, here I also decided to look what is the variation in different dimensions. So then if you look on this object and we say that, okay, this is the length of the object and its desired value, nominal one that we designed in the CAD model was 75 millimeter. Then we say that we have width. You can see it also on the screen. Width is 10 millimeter by design. And then we have thickness. That was supposed to be 2 millimeters by design. And then you can see on the graphs in which the red dots corresponds to this tolerance that was told to us by someone who recommends to use this value. And I decided to see, are there any deviations that are larger than this tolerance range or no? And as you can see in length, everything is inside, so it means it's not that bad. Thickness, it also lies quite tad and a bit closer to 2 millimeters to the desired value. Not that bad. But what about width? Do you see any problems here? Is it this 0.5 millimeters? Do we follow this rule? It doesn't look like that, right? It looks like we got really like larger parts, and we don't want to have this behavior. We want to be aware at least that it can be like that when we make something. Imagine that you have a shelf in the kitchen and you want to put something in the shelf. You measured it, you designed, you 3D printed, and then you try to fit it in and it doesn't go. It doesn't fit and that's all. What should you do then? Of course you will go, change design and print it again, right? You will try to measure how much it doesn't fit. But imagine that you want to fit inside a shelf in which you want to have some stuff. Then it's more critical, right? These tolerances and dimensions. Then you want to be aware what can be the deviation. And what actually affects, because we produce all those parts that I analyzed, it was 35 samples like this, produced in one run. So I fitted them on the build plate as you can see on the screen, and I just hit run. How can it be that in one run I produce 35 parts that has different dimensions, that actually have deviation? What does it mean? And then I decided to help you a bit more and show a bit another representation of the same graphs that you've seen before. So as you can see, for example, that our desired value was 10 millimeter for width, but actually we don't hit this 10 millimeters at all. We have all parts that has larger widths than we wanted, all of them. So interesting, right? And then thickness. Ooh, here we can see a huge distribution. A bit here and there. Why does it happen? We produced everything on the same play, at the same day, at the same time. Strange, right? And then lengths. Here we get even smaller than we want parts, or larger. So the problem is all of this, in that material has a special behavior. And while we are doing printing, some layers keeps being hot, while other layers starts to cool down. And then after we are done, the material shrinks a bit, and in some parts it shrinks much more than in the other ones. And that's why we have this quite different deviation all over the place. But then the question is, can you do it at home by yourself? Can you trick this part and decide, okay, this time the deviation will be such, and then later it will be a different one? Most probably no. So this is what I do in my research. I'm trying to develop such algorithms that later, hopefully in the future, can be transformed in regular mobile applications that will allow you to scale objects automatically by just telling the software where the object, in which printer is printed, which material it uses, and where it's placed in the build plate. So this is what my research was about. Can I scale each object individually when we print more than one? So this was my... So that's why I said it's not really academic presentation, but this is actually what I do. This is all my research. So at this moment, we have more than only this task. Together with my colleagues in our lab, we actually are working on the development of smart monitoring systems. So then hopefully someday you will get this app that will allow you to control and scale parts. On the way, for desktop 3D printers, we also have the same project, but for industrial machines, and I will show you just on the next slide how they look, these industrial machines. We also work on the algorithms to do a quick dimensional quality inspection based on the 3D scanning results. So imagine this minion. How should you treat dimensions here? Do you have a regular lens? What about crown? What about arms? How are you gonna measure the quality? How are you gonna define that it's a correct one? And imagine then you have some industrial part that is inside your car or inside the plane. Of course it's challenging. So we're trying to develop some algorithms in order to use 3D scanner as an object to provide us models to compare. And then the last, because a lot now we talk about all these monitoring systems, but then it means that we are going to use sensors and stuff. And that's why we need to take care about cybersecurity issues for additive manufacturing. So if you have an app on your phone or at home on your computer, that no one gets to you through that app, or no one changes parameters on your printer through that app. But then, as I promised, just to show you which printers we have, industrial printers we have in Avalab, and actually we have one metal printer and then one polymer-based printer. And this polymer powder-based printer, this is my baby. I played with it through all my PhD. So it wasn't the desktop 3D printers that I worked with, it was those machines and the issues connected to those machines. And then when we talk about those machines, the difference is that in desktop 3D printer, we talk about build plate in which you can kind of consider it as a 2D space where you put your object and you produce. And in polymer powder bed machine that I was working on, you can see that you can fit, you have a big box in which you will make parts, and then you can fit them any way you want. It just you need to make sure that you will get the result you desire in the end. And this was my task. If you pack it like that, how actually you can get each part at the same desired value as we designed them. And another difference is that in desktop 3D printers, we use polymer filament, but in powder bed machines, we use powder as a material. And just for your comparison about the powder, you can see on the screen that we have this large yellow circle, and it corresponds to the castor sugar that you have at home. And if you drink coffee or tea with sugar, then you use this one. Then you have a human hair from the microscope size, and then the material, powder material that we work in, it's in this size. So it's even smaller than our human hair, just for you to imagine what we're talking about when we talk about material. So this is a small introduction to my world, and I hope it encourages you to get to know printers better, and you know that you can use our printers in the lab. You can go through the course, and then it's open for everyone at NTNU, not only Jovik. Thank you very much.
Thank you very much, Ivanna. I think we have all learned a lot, even those of us who are not very familiar with your topic. Do we have any questions from the audience? I brought my laptop, and that's because we have some comments and some questions. And not surprisingly, the interaction design people are very interested in this. And I'd like to bring to you a question from a colleague of ours from the Department of Design, Kjell-Are Refsvik. And he asks, could you suggest a low-threshold sailing CAM model software for non-engineering students that wants to get started in 3D printing? And then, could a web-based software work here?
Actually, when we talk about, I just tested it. So Autodesk has web-based solution, which calls Tinkercad, tinkercad.com. You can go there. They have a possibility of designing CAD model in a very simple way. So kind of as a starting point, where you operate with 3D objects and then you CAD or add on other 3D shapes. So this you can use after you designed your model. You extract it as a STL file, or if it's not possible, then it's step file resolution. On the web site, on the online, you can also find the free converters from step to STL, and then you use printer software to slice it and print it. That's all. So it's like you don't invest any money in that at all. Everything is free of charge.
Thank you. I hope that was an answer for you, Kjell-Are. He also says it's a very interesting run-through for 3D printing. And for me, myself, it was a crash course. And it was very, very nice.
We have, in Norwegian, we just launched net-based, online, web-based, online course for 3D printing, but it's in Norwegian. But actually now we are having agreement also with the lab that they will provide at least some personal course here for now in English, but in the future we'll also develop the similar course for 3D printing in English, and especially who is present in Gjøvik. It will be quite easy because you go through the course, it's gonna take a couple of hours, maybe 1 week max, and then you can go and use our printers in the lab. For those who are not in Gjøvik, then contact me and we can talk.
Thank you very much. There are no further questions on the YouTube chat, but I'd like to thank you. We have some chocolate and we have a squeeze ball designed as a brain. You'll have that one. But first of all, thank you. We are about 20 people here, and there was also 30 persons watching you at YouTube now for this section. I'd like to wish you the best of luck continuing your research on this additive manufacturing theme, and I think it's very important for us to have young researchers within this area. So thank you very much. I hope you'll all watch us again tomorrow. There'll be a new researchers' lunch tomorrow about another theme. I think it's medication. So you're all very welcome back to tomorrow at the same time. So again, thank you, Ivanna. And I'll bring you your chocolate and your another brain, your squeeze ball brain.
Thank
Just
you very
a second.
much for inviting me.
Thank you very much.
Oh, thank you.
Good luck. This is the brain. So thanks to you all. Bye.
Thank you.